Okay, here's the last video for class 10. I'm doing this for completeness. I want to take a look at a more complicated example using Stanisic's mechanisms and machines. So this is like the example that he uses for several different things. It's a more complicated, it's like a 4-bar combined with a slider crank or crank slider, whatever you want to call it. So it has two vector loops. And so we have two vector loop equations right here, and the first one here is going to be about this base, about this basic 4-bar that you'll see down here. And the other constitutes where we have this an additional ground vector 8 comes through this, like you could think of as a I guess sort of like the crankshaft kind of thing onto there. And it goes through this little sliding area 5, right? And so you can see with the arrowheads that it's coming in the positive direction of 6, but then going backwards through 5. 5 and 7 are forced to be perpendicular to each other, and 7, I believe, is a fixed magnitude, but its angle can change. But what can't change is its angle with it has an angle that's attached to 3. Okay, that's right there. So it's like a fixed angle that's meant to be there, this gamma type of thing. So it's kind of like stuck there. It's not necessarily, it's perpendicular at 5, but then its angle is stuck there. So 7 is pretty much kind of fixed in place, or it's established by the other links. And then it comes back through 4 and back through 1. So 4 and 1 it shares in common in its vector loop. But there's also, we'll see that there could have been a third vector loop that we could possibly make, but that would be not an independent equation. So there's really just two equations, two vector loops. And we could break it into x and y, the first vector loop, and then the second vector loop, we could break it into x and y. So here they are closer, and we can see that we have the unknowns, or the knowns, excuse me. Theta 1 is 0. That's going to be the ground length, so we're going to assume that this is actually horizontal, and everything else shifts up to rotate with it. And, excuse me. So we know all these different lengths. We know all these different positions. The unknowns is theta 2, so that's we often will that will be the input often for the thing. Theta 3. We don't know, and theta 4. So those are the common ones that we have for the 4-bar. But now in addition, we have the angle of 6, that's unknown, the distance of 5, also the angle of 5, so we can move about this way right here, and the angle at 7. But as I mentioned, we've established that the angle at 5 is going to be perpendicular to 7, so there's an additional equation. And then the angle at 3 and 7 are related by this gamma. So there's 1, 2, 3, 4, 5, 6 equations, and so we have we've added to the knowns right here. So let's see. So the unknowns, we have 1, 2, 3, 4, 5, 6. So there's 6 unknowns and 6 equations as soon as we have a theta 2 as an input. And so we're going to go through a process where we guess at a solution, and then we find the answer at that guess, and we compute a new one from the equation right here, and then we compare the two, and we come back and we update, and we go back through this loop until we're done. So here they are describing it. The process. So here's the f right here. So here's the function. Here's the 6 equations, and so we're calling those the functions. And here are the variables that have been set up. So we put them in a row, and then we create the Jacobian by taking the partial derivative of each of the each equation with respect to each of the variables. So we set up, and this is a 6x6 matrix. And so here's our initial guess that we put into the thing. And we have after we get done, we find here's the next guess, here's the next guess, here's the next guess. We go through these iterations. Here's what the answers are going to be in radians right here, right? So in terms of a code, a MATLAB code, for whatever reason they decided to define what pi is. Pi is a built-in function, but I don't know why they did. But we did establish gamma. We gave them all of these scalar knowns. So these are the parameters that were used in the example right here. I decided to make it into SolidWorks. So right here is what that looks like right there, right? So you could see here is the input that's 3 inches long. And here is, so here's vector 1. Here's vector 2, which is the input, and I haven't established its input angle yet, so I wanted to make sure that we could make the thing move. But you could see here is how this thing moves. When it comes up to a certain point, it comes up to there. We can see that it's not going, there's going to be a certain point where it's probably going to go too far, especially to be able to have some range, because if you take a look at the original doohickey, I think he's up here somewhere. Let's see, I'll come back up to here. Nope, I'm going to come back up to here. Where's the doohickey? They're not even showing us the doohickey anymore. Where is it? Where'd it go? There you go. You can see that eventually this thing is going to have a range that can only go through so far. So you have to make some decision as we start to move this thing, into its angle right there. See, it starts getting longer. It can only get so long. So it's probably going to rock back and forth or something along those lines right there. So you see that's 3.9. So let's take a look at some of the other lengths. 3.9. There's 1.4. Here's the 1.4. So you could believe that this is a mechanism right here, just in this little sketch. And once we put in the input angle onto the thing, we put this input angle. It's designated as an input angle of 58. So this is the final solution. You can see that it's completely resolved. So we have it all in black. And if now we want to find some of the other answers here, like we can have this guy. Now this is going to be overdefined, so we let that be driven. Here's one. Oh, nope, I don't want that. I want to make just a, this is the length of 5.78. By the way, let's get a couple more sig figs in there. 0.7849. Okay. Other angles, we can even check out his angle right in there. Whoop, nope. That's going to the middle. I wanted to make an angle. Here to here. Ends up being 39. That's driven. What other angles? Well, we have the ones that we knew that we were going to get anyway, right? So those are. This is also, that's at theta 3. There's theta 4, right? So theta 3, theta 4. Some of the other unknowns that we're going to be solving for. We have R5, so we just got that. We got theta 5. That's this guy right here. Theta 6. All right, so that's going to be off of this root right there, right? So we're going to find that one's going to come back, and it's going to be this right there, right? So that's going to be theta 6 to be able there, and then theta 7. Where did we say? Theta 7? Theta 7 is probably going to be from here to right there. That's going to be theta 7, right? So here are those are all things that we know that we're going to be able to solve for. 3, 4, the distance of 5, theta 5 right here. So the position of this right here, the position of 6, and the position of 7, back and forth, right? So when we go into our we will be have that input angle. There's our 58 input angle. Here's the guesses that we made. These are like sort of intelligent guesses. We try to make the thing into a posture that could possibly exist. You can't just pick any old thing for your guesses. So make sure that we pick something that's possible. So we define the vector initial guesses. So there you go. We may turn that into a string and a column. And then we make a loop. So we're going to say there's going to be 5 iterations as part of this one. And we establish all the angles, so we get the cosines and sines of all of these, so that we maybe write it in a more compact form. Okay, there you go. So we got a bunch of them, and then we compute the functions at the guessed values right here. So we made these initial guesses up here. So here are all these equations, and here they are right here. So here's that functions 1, 2, 3, 4, and then the other remaining ones are those angles that have established themselves. So now we define the functions. We make a function variable right in here, and now we have the partial derivatives. So all these are written out as columns, and then we arrange them into a matrix where we put them all into rows, right? So we take all those columns and put them into rows, and then we use this equation right here, which is just a simple, straightforward dividing the thing out. And so it's saying equation 267, and let me see where that is in their book. Let me see equation 267. Where are you at? Equation 267. Interesting. They didn't show me where their equation 267 was. Right here. Oh, back up. I think they might be wrong about 267. I don't know where it is. Right here. No, they don't mean that, 267. They're a bunch of liars in the code. But this is a first edition, so who knows if they haven't fixed a couple things in there. By the way, this is their this is where I got the MATLAB code for. So this is what it looks like in the book right here, where they have they've defined the pi, and I just put the whole thing through into there, and what some of the comments are. Right here it says use equation 267 to compute that. So that's not true. I don't know what equation 267 is, but we'll come back to that. All right, so looking through here, and here are the okay, so we get some outputs and we're done with the thing. So let's take a look at what this looks like in MATLAB. I am in, okay, so I am now in the remote computer downstairs, and I want to open up my the equation, the MATLAB code. Thanks for welcoming me here. So Hartford, oh, was it blackboard.hartford? Blackboard.hartford.edu. Yay! Well, look how close a lot of computers. Sure, cookies are great with me. I like cookies. Doesn't everyone like cookies? You know what they call them in England? They call them biscuits. Cookies are biscuits. Go figure. Who knew? Well, now you do. So we go to the notes, and we go to class 10. And here is our class 10. And let's open it up. They're going to ask us what to open it up with, aren't they? Are they? Yes. We'll say MATLAB to MATLAB code. All right, so we're going to answer all of these. When we get to the end, though, let me get an angle. Let me get angles out from here. First off, something this just bothers me right here. We're going to get rid of. We're not going to define pi. How freaking arrogant do you need to be able to define pi? But here, we're going to go the angles right to the thing that we're going to define, similar to what we just did right here, right? I'm going to have the angles, and I'll define it by being what do we have to say? T1, T2, T3. So let me just go like this. I'll go. This is the output of this is T3. Okay, so what I really need is I need T3, T4, T5, T6, and 7 to be able to compare them to what I have. Okay, so I just hit run, and I will change what folder is in there. And so now when I call up my angles, here's what my angles. Whoops. Oh, I guess go down. Okay, let me just go snippet. Let me grab a hold of these so that I can easily just compare them over when I close out of this and come back to my thing here. Okay, and so maybe I want to break this down, bring this over a little bit. I just want to compare our results. I can't move. How do I grab? Grab right there. Okay, so I'll just put it in Paint. And put my little snippet in there. Okay, so I'm saying that theta 3 is supposed to be 19. Whoop, yep, we got it. I'm saying that theta 4 is supposed to be 105. Yeah, there you go. Woohoo, we're on a good track here. We already found out from, okay, so I'd never found what R5 is 0.78. For this guy right here, right? So I found him is 0.7849, and we had that 0.7849. Pretty impressive stuff here. Theta 6 was going to be, where is theta 6? It's up here at 330. Ooh. Oh, so we went to negative 29. So there you go, right there. That's same thing, negative 29. And then lastly, theta 7 is 129.79. Bingo, we got it. And I think I might take a little bit of time and actually make this into a real mechanism based on this sketch right in here. So I just like doing that. It makes me feel happy. So maybe I'll pause the video and do that, even though it's 8:23 at night, and I should be home. It takes an hour to get home, but I don't know. Just kind of interested to see what it's going to look like. So let's see how long it can take. It's this video is 18 minutes long right now, and so this is like a speed contest. I'll be back. I want to make this thing into a real thing, and so I just want to see what it looks like. Okay, so here it is. Here is my creation right here, and I will rebuild and save documents. And I decided to call this Stanisic Example 2.4. Is that right? Yep. And so here's the thing. Here's what this looks like. And if it goes too far in that direction, this thing comes up to there. Interesting, right there it can make it, but then it has a little, it could go this right here. So, and whatever that thing is going to do, right? Anyway, if we want to make it so we can go further there, I got to make that slot longer. If I want to go there, if I want to come up to past there, that slot has to be long. But that's what this thing looks like right there, back and forth. It's kind of an interesting little motion that the thing is making as it comes back there. So anyway, I wanted to see what this thing would look like, get a little bit of a better sense of what the motion would be like. And that's kind of what we do in mechanisms, to do a little what ifs kind of thing, and satisfy our curiosity into what these are going to look like. But now we've done it in a couple different ways here. We've solved it, well, I guess 2 ways. I've confirmed it that the MATLAB routine is working correctly, and we can use that to like maybe do some of the velocity and acceleration analysis as we go forward. So that's all she wrote into a 20-minute thing. I didn't time to see how long this took. Maybe I can go back and see if it took me 20 minutes, maybe something like that, to build this model. I was racing. So thank you.